Yes guys, today we're going to be going through the year 2 force diagrams from A-level maths. So we're going to start off simple with just an inclined plane. Let's switch to black. It's not got the option for that. Alright, fine. So we've got let's say a rough horizontal ground, and we've also got slope, angle, like inclined at angle, let's just say alpha. And on this slope we've got a just a box, and we can model that as a particle, but we just draw it as a box. And this box has mass of m kg. Now if you resolve the forces around this box, we've got weight acting downwards, and we can resolve the components of weight. So we know that this angle here is 90 minus alpha. Since this force this force here is perpendicular to the slope, we can say that this is alpha. So just get rid of all of that. Now just using some basic trig, we can say that this is mg cos alpha and mg sine alpha. Now if we move on and check out the reaction force, well, that just acts perpendicular to the plane it's on. So that's r. Let's call this r, little m. And we know we've also got friction acting on the slope. We got the float here. The slope has friction, therefore this friction acting against the box. So let's say our box is accelerating this way. We've got friction is also mu rm, and it's mu rm when we are in limiting equilibrium, so when it's when the box is on the verge of moving. And also we've got reaction from when the ground hits the plane. So we got RA, let's call this point A. And yeah, to be fair, we can leave this for another diagram. And that's as advanced as the most basic diagram gets. So now let's get the same diagram and have a pulley at the top of our inclined plane. And we also have a string passing over this plane, and the string acts parallel to our slope. So for alpha, get our box back in mkg. Let's quickly resolve our forces. mg cos alpha and mg sine alpha. We've got reaction. Let's call this. Let's switch A to let's call this box A. So we have mag, mag. We have reaction A, and well, let's actually draw on another box at the other end of the string, and this box here, well, it's only got its weight acting downwards, and we don't need to resolve this weight since it is simply vertical. So we have mbg, we've got tension acting on the string. So let's say this string is taut and it's light. That means tension throughout the string is the same, and the mass of the string is negligible. And the last thing to add is that this, let's say the pulley is smooth. Alright, that's fine. And well, let's say we've got a rough plane. Well, we know we'll have either friction acting this way if we're accelerating that way. So this is really in the case when the mass B is greater than the mass of A. Otherwise, if we've got A heavier, our particle usually accelerates down the slope. We've got friction opposing the motion, so we've got acting there. And we can resolve our forces. So we can take, I need to add that acceleration also acts, in this color, it's this way, and when A is greater than B, we've got it going that way. AMS minus 2. When we resolve, right, we start off by resolving perpendicular to the slope, parallel to the slope, and here we'd obviously use Newton's second law because we've got acceleration. Here we can simply just equate the two forces because there's no acceleration, and here again Newton's second law, and we can take either way as positive depending on which case we have. So it's simply be mbg minus t equals mba, and then we form two equations, right? Actually three. Now this equation here, we get some equation for RA which we can sub into this equation that acts this way, and we can simply just solve. So let's just go ahead and do that. So let's take one case when B is greater than A. So resolving vertically, we've got, okay, we said B is greater than A, so we're going downwards. We've got MBG minus T equals MBA. Now, since the string is inextensible, we can say that acceleration for mass A and mass B are the same. And B. Now, what about on A resolving again vertically? Let's label this equation 1 on A. So we've got T minus mu R A minus mg sine alpha equals equals ma. So mb a sorry, that's maa, not mba, maa. Now we can rearrange both for t, solve simultaneously, and from there we can get values for acceleration. Usually in the question we're given the masses, so we won't have that many unknowns. Normally we're just left to solve two unknowns, so that's all good. All good. And okay, I had a mistake here. I've actually resolved perpendicular to plane, not parallel to the plane. And if I were to resolve perpendicular, I would just have resolving perpendicular to plane. I just have RA equals MAG cos alpha. Right, on to the next diagram. We've got our beams diagram. So essentially, again, we've got an inclined plane, but it's resting on what we can call a sort of beam or a peg. Now, if it's resting, it's obviously got a reaction force. Let's call this point B, point A. And since we've got a rod resting on the ground, we can have reaction here. We have an angle which is inclined, the rod. And we're told that this rod is uniform. So that means the way it acts in the middle of this, so we have mg, and if you resolve, we have mg cos alpha, mg sine alpha, and well, we also have we have friction on the ground, and just say our rod to slip, our friction would act this way because our rod would be moving that way. So we have mu RA here. And we can resolve all these forces first, make this a bit smaller. RA, well, this angle here is 90 minus alpha, meaning this here is alpha. So we have RA cos alpha, RA sine alpha. If we resolve friction, let's call our mu RA up here, over 90 degrees here. Mu RA sine alpha, mu RA cos alpha. Now, if we resolve the reaction up here, we've got to do. Right, so we need to actually figure out the angle. Which one's 90 minus alpha and which one's alpha. So this angle here, right? This one is alpha, meaning that's 90 minus alpha, meaning that's just alpha. So all good, all good. Now we can just resolve again. R cos alpha, let's call this RB cos alpha, RB sine alpha. Now in this sort of diagram, 3 places to resolve vertically, horizontally, and the last thing is usually taking moments about A or B, depending on what the question wants. Now if you take moments about A, your equation won't have anything in terms of the reaction at A, neither the friction, and if you take moments about B, you won't have anything about the reaction going up here. Because why is that? Well, if you take moments about B, your equation won't include any of these forces because the perpendicular distance from B to all these forces is just 0. So that's nothing. All good. Now we're on a sort of like more complicated sort of diagram. And that is a ladder diagram. So we've got a ladder resting on a wall and it's inclined at angle alpha again. Point A and B is 90 degrees. Got a reaction here called RB. Let's assume that both walls are rough. So both surfaces are rough. So if the ladder slips, reaction will be acting that way. Friction will be acting that way. We've got reaction there, and we've got reaction there. So mu RB. And then we also have the weight of the rod. Of course, did we add that in the last? Yep, we did. Got weight of the ladder. Given that the ladder is uniform, we can just slap this bang in the middle. So if the length of the rod is 2A, then this would just be the length from A to where the weight acts is just A. Now if you resolve, we just have mg cos alpha and mg sine alpha. All good. So now let's resolve our other forces. So RA. So we've got we've got alpha here, and let me just verify that's right. We've got 90 minus alpha there, so there alpha, cool. So that would be RA sine alpha, RA cos alpha. Let's resolve friction, let's take that there. So we have mu RA. So we have mu RA sine alpha, mu RA cos alpha. And then we can resolve the friction on the wall. So let's just extend this, make it a bit bigger. Mu or B. And well, if you check the force out, this one, so the angle, this angle here is 90 minus alpha. Meaning that angle there is alpha. So we have mu or B sine alpha, mu or B cos alpha. Gosh, it's long. Finally, we've got the reaction. So we have So we've got angle alpha there. So we've got mu RA sine alpha. So RB. So RB sine alpha, RB cos. Perfect. Now, again, there's a few ways we can find values of forces. With this diagram, we like to take moments, so we can take moments about any of these 4 points. Now, if we were to take moments about here, know that our weight will be acting like this, if that makes sense. And the other way we can find forces by resolving vertically and horizontally, even perpendicular and parallel to slope. So we can go like here, 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 or we can go vertically up, or we can go we can go parallel to there, and there. All easy stuff. And finally, last diagram, we've got this sort of hinge. That's why I like to call it diagram. So we've got a wall, and this is our wall. And we've also got a rod here. This is our rod. It's being held by some string. Now the forces going on here, obviously you've got the mass of the rod, got tension in the string. Oops. And what else have we got? We've got we can say we've got a reaction force from the wall acting on this. That would just be here. So we can go that R, let's go to point A, RA. And let's just resolve our forces. So we've got, it's nice and big. We've got, where's the alpha? We've got alpha there, so that's alpha. This is T sine alpha. Obviously going upwards. And we've also got T cos alpha. We can also resolve mg. Let's do that real quick. So we've got alpha here. So we have, you do mg sine alpha, mg cos alpha. Now the wacky thing with this diagram is we've got a force, or a frictional force of the wall. Now we're wondering, where does this act? Well, let's think about it. Friction acts vertically, so the forces to consider are T sine alpha, mg. Now if T sine alpha is greater than mg, well, to compensate for this like imbalance, we want to increase the force that's got less of a magnitude. So in this case, that would be mg. So here we'd have friction acting this way, U RA. Now if it was the other way around, where mg was greater than T sine alpha, we'd have friction acting this way. Now these sort of questions, they might ask you, well, find the magnitude of the reaction force, or the forces on the wall. Well, that's just these two forces, so we just know we can take Pythagoras of that. Now hypotenuse will be the resultant force on the wall. That's all for these diagrams. Goodbye.